Alrighty folks, today we begin our journey into the Matrix. Not with Neo, unfortunately, but we will be doing something almost equally as cool. So, in terms of what we are going to do with matrices, we're going to look at the basic operations to begin with. So, we need to set up our foundational knowledge of matrices. This can be a little bit overwhelming to people just because they look scary, but I promise you they're not too bad. So, as we go through this chapter, we're going to get a little bit more complex. We're going to start out with the basics. So we're just going to start out with how we talk about these things and what a matrix even is and what the plural is. So when we talk about a matrix is just a rectangular arrangement of numbers. We have our rows, so rows go left to right, and our columns, and that's up and down. So when we talk about the dimensions of a matrix, we're always going to talk about it in terms of rows and then columns. So think about like an RC car. So my RC car is going to be rows and columns in my matrix. So when I look at this, when I talk about the dimensions of this thing, the dimensions are going to be 2 by 3, right? So my 2 rows here, and then my 3 columns right here. So 1, 2, 3, and then my 2 rows along the side here. Again, when we talk about multiple matrix, we talk about matrices. So that's the plural there. When we talk about an entry, we talk about a single value in this matrix. When we talk about, say I want to talk about row 1, column 1, I'd be talking about the number 6. If I want to talk about row 2, column 1, I'd be talking about this value here, the -2. So we count down and we count to the right for our rows and columns, respectively. When we look at these things, some of them have a special name. It's not often that we use this, but it's kind of cool to call it out now. A row matrix is that of which only has one row. Column matrix, that of which it only has one column. A square matrix has the same number of rows and columns, and we'll talk about these things later on. A zero matrix is just where all the entries are 0. And then we have 2 matrices are equal only if their dimensions are the same and the entries in the corresponding positions are equal. Okay, so if I had something like this, I'm just going to draw a quick 2 by 1 matrix. I'll even enter the values 2 by 1. This thing would be equal to a 2 by 1 like that, but a 2 by 1 like this is not the same thing as saying 1 by 2. And it doesn't matter that I swap the position of these things, it's just saying the rows and columns, the dimensions, don't match up. So first and foremost, that's an issue. And the second is, even if I do have them, whoops, a little overzealous on the matrix there. Even if I do have them line up, so 1, 2, 3, 4, and then I want to say is not equal, so down here we said not equal to, if I just swap them around. So even if I just swap the 1 and the 2 and the 3 and the 4, right? So if I were to swap these 2 columns, these 2 are now no longer equal matrices. So when we compare matrices, we're going to look at if they're equal based on the dimensions, and then after that we're going to look at the actual entries. So dimensions, the one on the left here is 2, so rows, there's 2 rows, and then I've got 2 columns. So the dimensions for this thing is going to be a 2 by 2. And now I'm going to go a little faster now. I look at this one because I see it's the same, 2 by 2. So I do have a good matchup in terms of my rows and my columns. And now I want to look at the entries, okay? So the first one here, I'm looking at 5 and 5. Those are the same. That's good. 0 and 0. Those are the same. That's good. -4 over 1, which looks different but is actually the same as -1. We just simplify the 4 over 4 to be 1. And then 3/4, which is 0.75. One thing we want to be careful of here is if this were reversed, say this is like 4/3, I wouldn't have it equal to 1.3. That's rounding, so those two are not equal, but 3/4 and 0.75 are equal. So this one is good to go. We would say that these are equal. The one below it here, we would say they're not equal because the entries are not the same. 2 by 2 and a 2 by 2, so I like that to start. But now as I start looking at this thing, -2, -2, that's good. 6 and 6, that's good. 0 and 3. The corresponding, meaning in the same relative position, are not the same. And I have it happen again over here. Double bad. If you want to add and subtract matrices, they need to have the same dimensions. All of the corresponding positions will be what gets added together. So I'm going to illustrate in color here what I mean by that. The first one that we're looking at is problem A. In problem A, as we look at this, I've got 3 rows and 1 column. So this is a 3 by 1, and this is a 3 by 1 as well. So now I can say yes to the addition here, and so when I add these together, what's it going to give me? It's going to give me the same excuse me, same dimension as what I started with. So I'm going to end up with a 3 by 1 matrix like this. So I'm trying to draw it out a little wide here, but hopefully I've given myself enough room. I'm going to have the entries here in green, and I'm going to have the entries here in blue, and I'm going to show you what exactly it is that we're doing. I'm doing the first row, first position, plus the first row, first position here, okay? So here I've got my 3 plus 1, and then below that in my next row, I'd have -4, and we would say plus 0. It's not a very good negative sign, but there we go. And then the last one here we have 7, and we will say plus 3. So now as my final step, I'll write my answer over here, and I'm just going to simplify. So last time I checked, 3 plus 1 was 4, -4 plus 0 is still just -4, and then 7 plus 3 is 10. I'm good to go. And we see the step-by-step down here as well, just a little bit easier with the colors. So looking at the next one here, we have subtraction. So looking at problem B, I'm going to scroll down a smidge here. I'm going to just highlight the fact that I've got this 8 in this first row, first column, subtract this 2 in this first row, first column. I'm going to highlight that in red here. It definitely can get a little bit confusing when we look at these values because like the spacing is very difficult to tell sometimes, especially when we first start doing these. But this is saying 8 minus 2, and that's the first row, first column position here. That also is referred to as an address. So when we talk about like what row and column specifically it's in, if I said, 2, 3 is the address, it's my row 2, column 3. So just FYI, if I say address, that's what I'm talking about. So we have that this one added up here, 8, added up, we're doing subtraction, but 8 minus 2 is 6. Then I'm going to go through and highlight in orange here, we've got 3 minus a -7. Okay, keep in mind that we are doing subtraction here. So if I go 3 minus a -7, that's really going to turn into addition. So I guess I should maybe underline down here to stay consistent, but there we go in orange. It's going to add up to give us 10. Here I'm going to have my 4 subtract 6, which will give me -2. And then my last one here, I'm going to do the 0 minus a -1, so that's going to turn into addition for a +1 value. So this is my final answer for the subtraction of those two matrices. For the last one here, we love it when we get problems like this because I look at it for, 0.5 seconds. I say this is a 2 by 2 and this is a 2 by 1. Are they the same dimension? No. Can you add them or subtract them? No. We're done. That's it. So in matrix algebra, we can do this thing called multiply by a scalar. So when we multiply by a scalar, we're basically doing our distributive property, or most oftentimes people think of it this way, is we're doing our distributive property into a matrix. So this 3 on the outside here is going to hit every value inside of the matrix. 3 times -2 gives me -6. That's going to go in my first column, first row, first column. Now I'm going to do 3 times 0, just gives me 0. 3 times 4 gives me 12. And then 3 times -7 gives me -21. we can see the step-by-step for that just below here. So I didn't write out, I just read it off as I went, but this is explicitly written out here, and we see we get the same answer because we're awesome at math. Here I've got a two-step problem, and there's a couple different ways you can approach this too. So when we're looking at this, the first thing we want to do is hit our scalar multiplication into everything in this matrix, and then I want to add these two together. So when we're doing this, let's just scroll down a smidge here. It's not going to line up exactly where I want, but that's okay because we can just go off of this one down here. I don't know why I'm going back and forth so much. So here we go. We're going to do the -2 into this matrix here. So -2 times my 1, -2 times 0, -2 times -4. It's going to give me the following. So as I go through here, it's all of this step by step by step by step by step by step. Gives us all these, oops, highlighting the wrong thing there. Gives us all these values right here, just simplifying as we go. And now once I've done my scalar multiplication, I'm just going to do my matrix addition, just like we did before, right? This is a 3 by 2, this is a 3 by 2, so I can add these things together. So now I'm going to look at first row, first column, first row, first column, and I am adding these things together. So -2 plus a -4 is really a -6. And I'm just simplifying these things as I go. So in terms of when we're using our matrix operations here, we can also use those to solve for different variables. I'm going to show you the most simple example we can start out with here. I'm going to draw a matrix. I'm going to call it 1, 2, 3, 4, just a simple 2 by 2 matrix. I'm going to say it's equal to matrix X, Y, 3, 4. And I might ask you to tell me what X equals and tell me what Y equals. Well, in this problem here, it's about as easy as it gets. The first row, first column matches exactly right here, so that's nice. X equals 1. And then we have our first row, second column matches up with our Y. Y value is 2. Slightly more interesting would be if we saw something like this. Let's say we got 3x, actually let's do 3 and 2x equals 3 and 10. So now what I do is I set up the same as I just did before. 2x is going to equal 10 when I'm solving, and I'll just do some algebra. So 2x equals 10, divide by 2, divide by 2, my x value equals 5. So that's how we're going to be solving for variables when we're using matrix operations and equations. So when we look at this problem here, there's a couple ways we can do it. First is that we can take the approach of doing scalar multiplication into my first matrix and into my second matrix. Totally fine to do that. I personally am lazy, please don't tell anybody, but I am, and I don't want to do that scalar multiplication twice because then I'm going to have to add it up anyways. What I would rather do is add first and then do the scalar multiplication. So I'm going to show you what that looks like following this work here, and I'll mention that we can also do the scalar multiplication below. So just starting out with what I would do because I'm lazy. So as we look at this thing, my first step is going to be inside of my parentheses. So pay careful attention to where these parentheses are, right? So here I've got a big set of parentheses on the outside here. The 2 is going to both the things inside of it, just like if we were using our distributive property. So I'm just going to write 2x plus 3y. If we're using our distributive property, the 2 goes to both of them. So we get 2x plus 6y. Just FYI, we've definitely done stuff like this before, so it's not really much different. So now I'm going to say, okay, well, let's add these things up. I got 3x, -1, 8, 5, 4, 1, -2, and -y. Now, again, it's a 2 by 2 and a 2 by 2, so I can add them. And from here, it's just going to be top left, top right, bottom left, etc. So as I go through, that's my first step here. So the first step is to add these two matrices together, and it brings us to this point here. Now, important to note is that we were also told what this matrix equals. So we have another set of answers on the right side here. So when we're solving this problem, we basically want to get to a point where we can set these things equal to those numbers there. So my first step is done. My second step is to do the actual distribution now. So now I'm going to send it into this matrix. It's going to go to the top left, top right, bottom right. When I do that, careful, so remember to put parentheses around this thing. You don't want to just do 2 times 3x and then leave the plus 4. It's 2 times the entire thing, the 3x plus 4. So this should become 6x plus 8, and then you continue through it. 2 times 0 is 0, 2 times 6 is 12, and then 2 times 5 minus y is going to be 10 minus 2y. So now I get to a point where I can solve using this bit right here in green, and we'll do this bit right here in purple, okay? So the green part that I'm concerned about is top left to top left. So let's set up the equation. The equation should look like 6x plus 8 equals 26. From there, we're just solving with our Algebra 1 skills, and we get x equals 3. From here, I'm going to set up the same way. I've got my 10 minus 2y is equal to 8 here. So let's set that up, and then we just solve for y, so we get y equals 1. Now again, I personally would not do it this way, but you can if you would like to, which is to take my 2, which is a scalar for everything inside, and I can send it into the first and second matrices. So 2 times 3x, 2 times negative 1, 2 times 8, and 2 times 5 is going to bring me right here. I'm also going to do that same thing, sending it into the second matrix here. So sending it into the second matrix, 2 times 4, 1, negative 2, negative y, brings me here. Last step is just going to be adding these two things together. Once I add them together, I'm now at the same final step where I'm going to set them equal to whatever the thing on the right was. So my original equation gives me that. A few properties of matrix operations. So when we're looking at these things, we have our associative property. Basically just says, okay, if I've got a couple things to do, does it matter if I do this stuff first and then this? Or do I have to do them in some order? And it doesn't matter. Whoops, I'm a little stuck here. Technical difficulties. So when we look at this, it doesn't matter. So if I add these two matrices up and then add the third, that's the same thing as if I were to take the 2 and 3, add those up, and then add the first. Our commutative property is the same as well. It doesn't matter the order I add them. A plus B is the same as B plus A. When we're using letters like this, A, B, and C, these represent matrices. So we would see something like matrix A equals, I don't know, 2, 3, 4, 5, right? And then matrix B equals, I don't know, 1, 0, 2, 5. Oops, not the best 5. And then if we're adding these things, basically I'd be doing, 2, 3, 4, 5 plus 1, 0, 2, 5. And I would say, okay, it's the same thing as saying 1, 0, 2, 5 plus 2, 3, 4, 5. So again, just swapping these two things, just trying to tie it to a concrete example here, because sometimes the letters can throw people off. When we're using multiplication for some or different stuff, it's the same. So it's just our distributive property. If I'm doing a scalar multiple into an addition problem, it just is still an addition problem. If I do scalar multiplication into a subtraction problem, it's still just subtraction problem. We did an example of this right up here. So now we get into where these things actually start becoming useful. So matrices are actually useful. You probably are not going to use them as you go to the grocery store, but it's in all the different things you enjoy. So matrices use vectors and everything, and so when we get into like computer generated images and graphics and all that stuff, there's just tons of matrices running in the background doing vector calculations and basically giving us all the cool stuff. So special effects and things of that nature. One of the other awesome ways we can use matrices is in organizing data. So if I gave us this word vomit in paragraph form, we are likely to glaze over it and then just kind of like zone out for a minute. So that whole paragraph is actually just this matrix right here. it's a much cleaner way of organizing the information and just saying, okay, there's two types of plans, individual and family, right? There's comprehensive, HMO, and then HMO standard and HMO plus. So these are the three different plans, and these are the two buckets. You're either an individual or you're a family. And I can compare that to data for next year. So this is the pricing for next year's stuff, and that's right here. And so why is that helpful to look at it like this? Well, if I want to know the difference, so I want to see next year's stuff minus this year's stuff, so I can see like change in prices, I can easily do that with matrices, whereas if I was doing it in the paragraph form, it would be like, okay, find the last number here, and then find the last number there, and then do it again, and do it again, do it again. It's just a much faster and easier, more efficient way of doing things. So we can organize this information into a 2x3 matrix. If you wanted to do this as a 3x2 or a 2x3, it doesn't matter. So this is illustrated as a 3x2 here. Again, 2x3 is fine. It doesn't matter one way or the other. It's just that your individual and family would be your rows, and then your comprehensive HMO plus, HMO standard and HMO plus would be your columns. It's going to present the same information either way. So that's just organizing the data. Now we're actually using it here. So to actually like look at how this would be helpful would be to say, okay, well, what is my monthly change going to be that I see in my healthcare plan? So when I'm looking at a healthcare plan, I'm looking at annual premiums here. So for the annual premiums that we're looking at, we're saying, okay, let's take this and adjust it to look at a monthly rate. Well, that's just going to be dividing by 12, right? So 12 months in a year. If I want my monthly rate, it's just going to be 1/12 of, and then whatever the difference was from year to year. So I'm going to just highlight in colors here. We have this year's stuff, and that's in red. And we have next year's stuff, which we'll highlight in green here. So basically, if I want to talk about the difference, like what is going to happen from year to year, I'm just going to do new thing minus old thing. And that's going to be my difference, okay? So when I'm doing this, the only additive that I'm including here is that I want monthly. So I'm saying 1/12 of that. And that's where this scalar multiple comes into play here. From here, it's all just addition, subtraction stuff. So here we're doing subtraction, and then I would do the scalar multiplication last. If you wanted to do it to both of these, again, totally fine. It's just one extra step, but it's ultimately going to bring us to the same answer. So this is really, really helpful because now I can say, oh, okay, so my monthly premium is going to drop by 87 cents for an individual comprehensive. So again, my monthly difference, just looking at individual comprehensive to start us off here, will be lower by 87 cents a month. And so you can kind of look at this and say, okay, who is this good for? Who is it bad for? There's a lot of like, actual, analysis that we can do using matrices in this form. The last thing here is, folks, whether we want to take the red pill and go to chapter 4.2 or take the blue pill, go home and take a nap. I'm definitely going red pill. See you guys next time.